In this video, we'll be looking at higher order derivatives. So we're used to taking the derivative of a function. But if we take the derivative of the derivative function, this is now called our second derivative. And we can take lots of derivatives. Now here's the notation. We know our first derivative might be y prime or f prime of x, dy dx. But when we get to the second derivative, we have f double prime, y double prime, or using the other notation, we have the derivative, so here's d derivative, of the derivative with reference to x, which can be written as d squared y over dx squared. So just some notation so that we know what we're talking about. So we have function f at x, which is this chordic function, and we want to determine the first, second, and third derivative. And here we're just using our nice basic power rules. So for our first derivative, we're going to have 20x to the 3 minus 9x squared plus 4x subtract 7. So bringing the exponent down and multiplying it by the coefficient that's already there and dropping the exponent power by 1. The second derivative, so I'm going to do a double prime. So I'm going to take the previous derivative and take its derivative. So 20 times 3, 60x squared. 9 times 2, 18x, and plus 4. And now I'm going to go one more time. The third derivative, so f triple prime. 60 times 2x minus 18. Now what I want us to notice here is that we started with the chordic function, and every time I found a derivative, that degree dropped. So if I have a polynomial function, every time you take the derivative, the degree is reduced by 1. So if I have a function that is to the power of 6, so a degree 6, and I want to know the shape of the fourth derivative, well, every time I take a derivative, the degree drops by 1. But if I'm taking 4 derivatives, it's going to drop 4 times, which means the fourth derivative will have a degree of 2, which means it will be a parabola. All right, let's find the second derivative of f at x. And this one has a root in there, so I might first rewrite this as 5x squared plus x to the power of a half. I'm going to take my first derivative, and we'll have 10x plus 1/2 x to the power of negative a half. And normally I would clean up my first derivative, but in this case, because I'm going to keep going to the second derivative, I like how it's looking right now. I want the rational exponent, so I can use my power rules. So now I'm just going to keep going. The derivative of 10x is 10. Bring the negative 1/2, so now it's negative a quarter, x to the power of negative 3 over 2. I'm going to clean this up. I want to get it as one fraction, and then I will find my restriction. So we have 10 over 1, subtract 1 over 4x. I'm going to keep it as 3 over 2, just to try to keep this as reduced as possible. So I want to make my exponent be an integer value, then I'm not having any issues. So if I multiply this by x to the power of a half, that would fix that problem, because 3 over 2 plus a half is 4 over 2, so it'll just be x squared, which is nice. Now, if I had written it as the square root of x cubed, I probably would have multiplied top and bottom by the square root of x cubed, which is totally fine, but maybe I won't be as reduced as I could. So I'm just going to continue here. So square root of x, subtract 4x squared. Now I see I should have a common denominator here of 4x squared. So I'm going to multiply 10 by 4x squared. And here we are. Now my denominator is saying that I can't be equal to 0, and my root is telling me I have to be greater or equal to 0. So, oops, we do not want to be equal to 0, so we'll just remove that. There we are. And there's our second derivative, some cleaning up. Now, sometimes it is helpful to clean up your first derivative before you go on to the second, but in this case, it was in a setup that I liked. Now, in terms of first and second derivative, the first derivative we know represents the instantaneous rate of change of f at x with respect to x, or it represents the slope of the tangent, and a tangent is at a specific point. The second derivative is going to represent the rate of change of the rate of change with respect to x. So it's the rate of change of this. So the rate of change of the rate of change with respect to x. Now, a very useful and common application related to first derivative, second derivative is related to displacement, velocity, and acceleration. So first, let's see the difference between those three things and those three functions. Displacement is the change in position, so the straight line distance from a starting point with respect to time. Now, the units you might see, meters, kilometers are common. It could be anything though. And the function is usually described as s at t, the displacement s with respect to time t. Now, velocity is the rate of change of the displacement with respect to time. So how much did the position change versus how much did the time change? So change in displacement over change in time. And that's going to be, the units are going to be maybe meters per second or kilometers per hour or kilometers per second, something distance related over something time related. And the function we use for that is v at t for velocity. But because velocity is the rate of change in the displacement, it's the first derivative of the displacement function. And finally, acceleration is the rate of change in the velocity with respect to time. So change in velocity over the change in the time. And the units we use here are meters per second squared, or kilometers per hour squared, or kilometers per hour per second, something like that. And the function we use is a for acceleration, which is the first derivative of velocity, but the second derivative of that original displacement graph. So first thing we're going to do is look at some displacement graphs and find some connections between the displacement, the velocity, the acceleration, depending how the curve of the displacement graph might look. So I have different curves here. Some are going up, some are going down. Some look like they're getting faster, some look like they're getting slower. So we're going to talk about it. We're going to make some observations. First, we're going to look at the tangent lines. If I draw tangent lines, do they look like they're going from steep to shallow or shallow to steep? So first thing, I'm going to draw it on. So let's say I have this point here, I'd say relatively shallow, versus this point here, it's getting steeper. So I'm going to say that they're just getting steeper. So shallow to steep. For the next one, it looks like I am steep, but then I'm getting more shallow. More shallow. The next ones, now we're going downwards. So the tangent lines will be negative, but I can still compare steepness here. So I'm steep, and then I get more shallow. And here, I start more shallow, and I end up steeper. Okay, so based off of this, does it look like the object is speeding up or slowing down? So because my tangent lines are getting steeper, I would say it's speeding up for the first one. It looks like it's starting off slower, it's more gradual, but then it's getting faster, it's accelerating. Whereas with the next one, it looks like it's coming towards a stop since its displacement in the long term is going to get a little bit more steady, so it's slowing down. And the next one, same thing, it's coming back to the starting point, but it's slowing down because it's approaching that more constant displacement. And finally, the last one, it's coming to the start, but it's speeding up to get there. Okay, now let's look at the tangent line sign. So is it a positive tangent line or a negative? In the first two, they are both positive lines. They are increasing. The last two, they are decreasing. The sign of the velocity. Remember, velocity is the rate of change of the displacement. This means that velocity is the derivative of this displacement graph, and the derivative represents the slope of the tangent. So because my tangent lines are positive in the first two, so is the sign of the velocity, and the tangent lines are negative for the last two, so the velocity is negative as well. These two are connected. Now let's look at the direction of the object. So is it going forwards or backwards? Forwards for the first two, backwards for the last two, because it's coming back to the start. And then change in velocity. So if I'm talking about the change in velocity, I kind of am looking at acceleration here in preparation to determine if acceleration is positive or negative. And for this, I'm going to create some fake coordinates for my tangent lines. So I'm just going to say here, this is time 1, this is time 2. And all of my random points I drew. I know I'm not to scale here, but I'm just doing it more for the visual. And at this time, I'm going to say the shallow slopes, the shallow tangent lines have a slope of 1, and the steep tangent lines have a slope of 2. So the tangent line, let me actually just switch colors here. The tangent line here is 1, the tangent line here is 2. The tangent line here is 2, the tangent line has a slope of 1. Here it's steep but negative, shallow and negative, shallow and negative, steep and negative. So I'm going to use these as my coordinates. This represents the time and the slope of the tangent line. So the time and the velocity for each point. And then I'm going to do a mini calculation just to numerically see what the sign of the acceleration will be. Okay. Just going to zoom out a little bit here. So our points are 1, 1 and 2, 2. So my slope is 2 minus 1 over 2 minus 1. That's 1 over 1. So positive acceleration here. Then for the next one, I have 1, 2, 2, 1. My slope, 1 minus 2 over 2 minus 1. That's negative 1 over 1. So the sign of acceleration here is negative. So in the forwards direction, it kind of, what you see is what you get. I see that I am accelerating. We said that we were speeding up, so we are accelerating here, and the sign of acceleration was positive for that first row. For the second one, I was slowing down. My acceleration is negative. But the minute the direction changes, you can't just think of, oh, positive acceleration, you're speeding up, negative acceleration, you're slowing down, because you're not thinking about the direction if you're just thinking positive, negative like that. So for the next ones, at time 1, the velocity was negative 2. It's fast, but we're going back to the starting point. That's why we're negative. And then 2 with negative 1. So now, being careful with my signs here. Negative 1 subtract negative 2 over 2 subtract 1. We have a positive rate of change here, so a positive acceleration, but we're actually slowing down. So we're not actually accelerating, but the sign of the acceleration was positive. We'll keep that in mind and make some observations after the final one. And for the final one, we start shallow, we end steep, but negative. So negative 2 subtract negative 1, or 2 subtract 1, and we have a negative acceleration. But we were actually speeding up here. So let's take a look. My sign of acceleration was positive, and my sign of velocity was positive, and we were speeding up. when else were we speeding up? At the end, where the sign of velocity was negative, and so was the sign of acceleration. So as of right now, it kind of looks like if the sign of velocity and acceleration are the same, we should be speeding up. Let's see if the opposite is true for slowing down. Sign of velocity was positive, acceleration was negative. Sign of velocity was negative, acceleration was positive. And for these ones, we were slowing down. Perfect. So let's put that together. Positive acceleration does not always mean speeding up. We have to look at velocity and acceleration. So an object is speeding up if the sign of velocity and acceleration are the same. And an object is slowing down if the sign of velocity and acceleration are opposite. So let's take this and apply it to a full-on scenario with a few other follow-up questions. So an electron moves along a straight line so that its position S with respect to some fixed reference point in picometers after t seconds is S at t equals that cubic function. The graph of S at t is to the right. So if I'm looking at the graph, here's time. It looks like this little electron is moving away in the positive direction. Then it takes a little pause. Then it comes back towards the start. So now it's back at the starting point. And then it leaves and keeps going forever. Okay? So based on this model, just visually here, when does the particle change directions? Here at 2 seconds and here at 6 seconds. When does the particle have positive velocity? Velocity is the first derivative of displacement. So it's pretty much just asking us, when are the tangent lines positive? Well, anywhere here, my tangent lines are positive. Anywhere here, they're positive as well. It's here between 2 and 6 seconds, when I'm heading back to the start, where they're negative. So the particle has positive velocity between 0 and 2 seconds, and between 6, oh, actually there is no stop here, so when t is greater than 6. And it has negative velocity between 2 and 6. Now, we're going to sketch a graph of the velocity function, and we're going to use the first derivative to confirm our answers. So right now, I do know a few things without me actually going to that first derivative calculation, and it's when the particle is changing direction. So at 2 and at 6, the horizontal lines are horizontal, which means at 2 and 6, velocity should be 0. The particle is stopped here, it's at rest, it's changing directions. But visually also, those look like maximum and minimums, which is where our tangent lines should be horizontal. I also know that between 0 and 2, my tangent lines should be positive. Between 2 and 6, they should be negative. And then positive again. So I'm expecting a parabola of some sort. But I want to be a little bit more exact with that, so I am going to find that first derivative. So the velocity is the first derivative, and it is 3t squared minus 24t plus 36. I'm just going to factor this to solve for my zeros algebraically, just to confirm, and then I'm also going to figure out the rest of this parabola. I'm going to factor out the 3. I'm going to crisscross or do the simple trinomial. 6 times 2 is 12. I should make them both negative though. There we are. So at positive 6 and at positive 2, I'm just going to set my derivative equal to 0 here. That's when the velocity is 0. So that change of direction. So I didn't need the graph. I could have done this algebraically. Find the velocity, set it equal to 0. And now, if I wanted to graph it a little better, well, I know that the vertex should be halfway between 2 and 6. So the vertex should be at 4. So vertex is 4. So I'm just going to set t equal to 4 in the velocity function, and I get negative 12. So I'm going to plot that point. Here we are. And connect the dots. And it verifies the fact that we should be positive between 0 and 2 and from 6 onwards. Actually, I also know that the y-intercept is 36 from right here. So I can do that as well, because we're not going to have less than 0 for time. Now, there is one more thing I can verify algebraically, and it's those positive and negative velocities. And I can just do a sign analysis. So I'm going to put velocity, and I'm going to create one of those kind of number line charts. So I'm going to go from 0 to 2, because that's when we change direction, from 2 to 6, another direction change, and from 6 onwards to infinity. And I'm just going to sub a test value between that interval into the velocity function, so that first derivative. So if I plug in positive 1 in for t, so 3 times 1 squared minus 24 plus 36, I get a positive number. If I plug in a value between 2 and 6, so for example 4, we already found the vertex, it was negative. And then anything greater than 6, if I plug in 7, I should get a positive. So I didn't need the graph at all. If I want to know when the particle is changing directions or when the velocity is 0, I set the first derivative equal to 0 and solve for time. If I want to know when the particle has positive or negative velocity, or when it's heading away in the positive direction or back in the negative direction to the start, I could have done a sign analysis. Now, let's look at this velocity function and answer some questions about acceleration. When does it have 0 acceleration? So acceleration is the derivative of velocity. So the slope of the tangent of the velocity function. Well, when is the tangent line horizontal? That's when time equals 4. So at 4 seconds. When does the particle have positive acceleration and negative acceleration? When velocity is increasing, it's positive. So all of these points here have positive slopes. So when time is greater than 4, and negative at the beginning until we head to the vertex. So from 0 to 4. We're going to sketch the graph of acceleration, and we're going to use the second derivative to confirm our results. So there's one point I already know. At 4 seconds, acceleration is 0. Then I know afterwards it should be positive, before it should be negative. So I'm expecting a line. But let's find that acceleration equation, or the second derivative of displacement, or first derivative of velocity. And I'm going to go to the non-factored form right here. And it's going to be 6t minus 24. It's a line. The y-intercept is negative 24. So I'm just going to draw a line like that connecting to the point I already knew. Perfect. Let's set acceleration equal to 0 to confirm time is 4 seconds. I'm going to factor out the 6. And here we are, t equals 4. If I wanted to see the positive versus negative acceleration, again, I'm going to do a sign analysis. So I'm going to have acceleration, and I'm going to go from 0 to 4, and then from 4 to infinity. If I plug in negative 1, I'm going to get a negative number. Negative acceleration, exactly what we predicted between 0 and 4. If I plug in 5, I'm going to get a positive 6 in this case. Positive acceleration from 4 to infinity, or time is greater than 4, like we predicted. So I could have done all of this algebraically if I didn't have the sketch in front of me. And now finally, let's determine when the particle is speeding up versus when it is slowing down. First, I'm going to look at our original displacement function to make a little prediction. Then I'll do it algebraically using velocity and acceleration. So just looking at the graph here, it looks like the function is speeding up a little bit, then it starts to slow down.
then it starts to speed up to here maybe, then it starts to slow down again when it's about to change direction. Then it speeds up, and I feel like it's gonna speed up forever. Okay, so let's see if that prediction is true just by looking at the function. Let's do it algebraically now. So we found above that if velocity and acceleration have the same sign, particle is speeding up. If opposite, it's slowing down. So I'm going to create a sign analysis here. I'm going to use velocity and acceleration. And in terms of the numbers I'm using in my intervals, I'm going to use the zeros of acceleration and the zeros of velocity. So I'm going to go from 0 to 2, 2 to 4, 4 to 6, and 6 to infinity. Okay, let's test our values. Let me just scroll up here so we could see the velocity equation, or just looking at our graph since we have it. From 0 to 2, velocity is positive. From 2 to 4 and 4 to 6, it's in the negatives. From 6 onwards is positive. I just looked at my sketch up here, but if I didn't have it, I would sub-test values in here, like we did here. For acceleration, any value between 0 and 2, I'll be in the negatives, 2 and 4 in the negatives. If I put in 5, I'll be positive. If I put in 7, I'll be positive. And now, let's see, when are the signs the same? Here and here. So we are speeding up. Oops. From 2 to 4 seconds and after 6 seconds. And we are slowing down when we have those opposite signs. So from 0 to 2 and from 4 to 6, which is kind of what I predicted visually, but now I have the algebra that backs it up, because we're not always going to have a visual, or we're not always going to have a simple polynomial, especially once we learn more derivative rules. So having this idea of speeding up is same signs, slowing down is opposite signs, a particle is stopped or is at rest, even if it's temporarily, when velocity is 0. So there we are. Here is a very nice application for first and second derivatives of the displacement function.